Welcome to the second lesson of our Redox unit. We're going to learn about oxidation states more thoroughly and look at different scenarios of half reaction equations that we kind of touched on last lesson. So we're going to first learn some rules to assigning oxidation states. The first one is that atoms in free uncombined element have an oxidation state of 0. So examples, you can have magnesium, oxygen, nitrogen, argon. All of these in their free uncombined elemental state are set to 0. In simple ions, the oxidation state is the same as the charge on the ion. So for the simple ones, you guys should know from Unit 3, learning from the periodic table, magnesium is usually 2+, oxygen 2-, and nitrogen 3-. The oxidation states of all the atoms in a neutral uncharged compound must add up to 0. So for example, if a compound doesn't have brackets with a negative on top or brackets with a +2 on top, then you know that the whole compound takes 0 charge. The oxidation states of all the elements in a polyatomic ion must add up to the charge on the ion. So here's an example where the polyatomic ion, so the compound essentially is an ion because of its 2 negative charge. So it has a -2 charge overall, and that's going to affect the oxidation state of sulfur in this polyatomic ion. The usual oxidation state for an element is the same as the charge on its more common ion. So group 1 elements we know usually are +1, hydrogen usually +1, oxygen usually -2. And lastly, most main group non-elements, the elements at the bottom of group 14 and transition elements, have oxidation states that vary in different compounds, depending on the conditions and other elements present. So here are the 6 rules assigning oxidation states, and they go in order, with the priority being number 1, and as we go down the list, we move down in priorities. Some useful oxidation states for us to look at. For example, lithium, sodium, potassium are +1 usually, magnesium, calcium +2, and as you can see, all the other ones are typically in its elemental uncombined state. They're usually -1, -2, +1, and -1. The first example we're going to look at is assigning oxidation states to sulfuric acid and sulfate. So let's take a look. So following the rules from before, we know that oxygen and hydrogen take priority over sulfur at this point. Sulfur was not mentioned in the top 6 assigning oxidation state rules. So we can say oxygen takes form of -2, hydrogen is +1. Like lesson 1 where we learned, we multiply this by their subscripts. So oxygen here is 4, hydrogen here is 2. We see that this is an uncharged compound. So because of that, we have to make sure that this entire thing equals to 0. So think about this. If we have -8 + 2, or 2 + -8, what would sulfur have to be? 2 + -8 plus something must equal to 0. So here, 2 - 8, -6, so we have to +6. So in this case, sulfur equals +6 charge. Similarly, we can do the same thing with this polyatomic ion. Oxygen holding -2, as it has priority from the rules. Multiply this by 3. We know the overall charge has to be -2. So in this case, it's not 0 anymore. The overall charge needs to be -2. So what do we need to add here? give you a moment to think about it. So here, let's take a look. This is -6. We want it to be -2, so we must add 4. So for this case, the sulfur in this polyatomic ion, it has a +4 charge. So now let's give it a try. If an element has a reduction of -2 and another is reduced to -3, what do these numbers really mean? So if an element, their superscript is -2, and another element, and another is -3, what do these numbers mean? So let's go to our Nearpod and answer this question. Hopefully you guys got a chance to answer this problem. I'm gonna move on to the next slide and have you guys answer another question on the Nearpod. Which species is oxidized and which species is reduced? Here's the chemical equation. So what's interesting about this now is that we know how to assign oxidation states to various compounds. And these different compounds, because they have different oxidation states, you need to remember to mention them when you name the compounds using their oxidation number. So let's take a look at the first example on the top left-hand corner. Iron oxide. Instead of just saying iron oxide, you need to make sure that if the iron has an oxidation state of +2, because as you see from below, it could also hold an oxidation state of +3. You need to make sure to mention that it is iron 2 oxide or iron 3 oxide. Similarly, let's look to the right-hand side. There are some other formulas of compounds. You can't just say manganate ion for the first row. You must say manganate +7, so manganate 7 ion. And it's an ion because the overall compound has a negative charge. So you need to mention that it is an ion. So now let's give it a try. Return back to your Nearpod and deduce the oxidation states of the following compounds. Remember, like what we just went over in the previous slide, remember to mention what oxidation state the compound is in. Now we're gonna go back to our half equations from lesson 1. So recall the oil rig example from the first lesson with magnesium and oxygen forming magnesium oxide. Recall that we were able to write out 2 half equations. So my next question is, can you write the half equations for this new reaction that we have here? So locate your Nearpod again and try to figure out the 2 half equations, recalling the method that we used in lesson 1. So what if a reaction now includes oxygen? In order for you to balance the equation, you can't just have 2 half equations anymore, right? You have to include the oxygen. But you can't just write a 3rd half equation for oxygen. So now we're complicating it a little bit, writing half reaction equations with oxygen in the chemical reaction. So here are some rules. Just like the oxidation state, these are prioritized as well. So the first one is we assign oxidation states to determine which atoms are being oxidized and which atoms are being reduced. Then for us to write the half equations for oxidation and reduction, we balance the atoms other than hydrogen and oxygen. We then balance each half equation for oxygen. So if there's oxygen in the equation, then we would balance the half equation by adding water, H2O, as needed on whichever side of the half reaction equation. We would then balance each half equation for the hydrogen because now we added hydrogen into the half reaction. We need to include the hydrogen ions in the other side that you included the water on. Balance each half equation for charge by adding electrons to the sides with the more positive charge, and check that each half equation is balanced for atoms and for charge. We then equalize the number of electrons in the 2 half equations by multiplying it appropriately so that we cancel out the electrons like we have with magnesium oxide previously. And then we add the two half equations together, canceling out anything that is the same on both sides. So all of this is a lot of information. We're going to take a look at an example. So this question is asking us to write an equation for the reaction in which nitrate ion and copper react together in acidic solution to produce nitrogen oxide and copper 2+ ions. So we have to first write out what the reactants are and what the products are. So in this case, we have NO3- in aqueous plus copper we can see here that copper is being oxidized, right? Because it went from 0 to 2+. So here copper is being oxidized. So in this case, if you double check yourself, you would notice that nitrogen here is the one being reduced. So now we know what is being reduced and what is being oxidized. We can first write out the two half equations. So the half equation of oxidation would include copper Remember from the last example that we used, we need to balance this out by canceling out, by adding electrons so that left and right overall oxidation states are the same. So we have copper on the left-hand side, which is equal to 0, so we need to make sure the right-hand side is balanced. It has a 2+ right now, so we need to add 2 electrons to balance this. Let's take a look at reduction. So this one is where it gets a little bit tricky because the nitrogen is together with the oxygen. So now you need to add oxygen and water and balance with hydrogen ions. So here, step 2, what we do is we can see that there's one more oxygen in the reactants than there are in the products. So in order to balance that, we have to add water on the right-hand side, on the product side. So in order to balance this, we need 3 oxygens on the right-hand side, and we only had 1. So we had to add 2 water molecules. However, now that we added 2 water molecules, we now have more hydrogen, and we don't have hydrogen on the reactant side. So we can see here we have 4 more hydrogens in the products. So because of that, we have to add 4 hydrogen ions to balance out this equation on the reactant side. So now let's make sure that this equation is actually balanced with the water and the hydrogen ions that we added. So let's take a look at the reactant side first. The overall charge for the nitrate ion is 1 coefficient times -1, 4, and +1 charge. This gives us an overall charge of +3 on the left-hand side. However, on the product side, we see that the overall charge is 0. So we can't just have -3 plus 3 on one side and 0 on the other. So what do? You got it. So we add 3 electrons on the reactant side so that both reactants and product sides equal to 0. Now that we have the 2 half reaction equations written, we need to balance it out. So for the oxidation, we need to multiply by 3, and for the reduction, we need to multiply by 2 so that the electrons are canceled out on both sides. Now that we multiplied it, we can cancel these 2 out. Now we have this final overall